All right, well, welcome to thermodynamics. I don't know what you think of when you think of thermodynamics, but thermo, I think of heat, but I think of heat, but it's really energy. And dynamics, right, means changes or it's changing. And so thermodynamics, we're not just talking about heat, although that is part of it. We're really talking about the energy and the change of energy. And also, energy can be viewed as the ability to do work. You know that work and energy have the same units? They are kind of interchangeable. Sometimes you can convert, right, energy into work or put work in to increase the energy. So, a few things that we'll be looking at this semester is the energy in heat, thermal energy, kinetic energy, potential energy, internal energy, then one more flow work we'll talk about. It's a little abstract, but it is the work needed for a fluid to flow into and out of a control volume, and then just work. But we're going to be looking at all of these, how they change. We're going to be keeping track of them, adding them, how much is going in, how much is going out, how much do we start with, how much do we end with. But thermodynamics is really the change in the study of energy of a system. There's classical and statistical. Classical is kind of a big picture thermodynamics, looking at the macroscopic level, looking at the whole fluid, the fluid as a whole, the control volume as a whole. Instead of statistical, is kind of looking at individual particles, thinking about the energy, the velocities, the energy of all the microscopic particles. Let's say microscopic. That's the statistical thermodynamics. This class will be classical thermodynamics. We're not going to get into the chemistry, the molecules, the particles. We're going to be looking at the fluid as a whole. Our class is based on these 4 laws of thermodynamics. All right. So we start with the 0th law. Why do we start with the 0th law? Well, I think that they had laws 1, 2, and 3, but then they decided before we get to laws 1, 2, and 3, we need this law. We'll call it the 0th law that says if 2 bodies are in thermal equilibrium with a third body, then they will both have the same temperature. I don't know why they needed to define that as a law. They did. What it just means is that if the temperature of fluid A is equal to the temperature of fluid, let's call it C, and if B is also equal to the temperature of fluid C, then the temperature of A would be equal to the temperature of B. Makes perfect sense. A little bit obvious. But that is the 0th law. If 2 bodies are in thermal equilibrium with a third, then those 2 have the same equilibrium. So we can kind of take a third to measure things, and if 2 things are equal to the third, then those 2 things are equal to each other. Okay. First law is conservation of energy. This is where we're going to sit almost the whole semester. Conservation of energy, keeping track of, if we keep track of all the energy can't be created or destroyed. It has to go in or out. It has to go somewhere. And so here is the first law. The sum of all the energy in, so sigma means the sum of all the energy that goes into our system minus the sum of all the energy that goes out. All right, so if we're keeping track of everything that's going in, keeping track of everything that's going out, like our bank account balance, right, then that would equal to the change in energy. We'd say delta E, change in energy. I would probably leave it as delta E, or we could say energy final minus energy initial, or energy 2 minus energy 1. All right, let's write this in words. the sum of all the work, heat, energy in, minus the sum of all of that work, energy, heat out, would be equal to the change in energy. So this is the final energy minus the initial energy. So if we're keeping track of, hey, it started right here and then an hour later it ended right here, then our ending energy minus our starting energy. Bauxite, I mean, we are going to see that again and again. That is what I want you to learn from this class, conservation of energy, how to calculate and keep track of all the energy going in, energy going out, and the change in energy in our system. And like we said, the last page, there's lots of different types of energy that we're going to have to keep track of. The second law is tough, a little more abstract, talking about entropy. And it says the entropy, or the measure of disorder of the universe, is always increasing. So it's just saying that naturally, things become less organized. Things become less organized. I mean, is that not true? In this house, in my house, I've got 3 kids, and naturally things are going to get less and less organized unless we put work into it, though. But if we leave it to be, this house is going to get less organized. If you leave it to, if you don't take care of things, right, things become less organized. It's kind of a measure of disorder. Things become more disordered. It's almost a measure of chaos. If we don't put work into things, things become more chaotic. This gives a direction for some processes. If we could measure the disorder, if we could measure the entropy, we know that naturally the total entropy is going to increase. Now, we might have pockets where the entropy decreases, pockets where the entropy decreases, but on a whole, if we look at the universe, or something that we could define as the universe, entropy is always increasing. One of my favorite quotes, let's see if I can remember it off my head, is, without hard work, nothing grows but weeds. That is a little bit about entropy. If we leave things to be, weeds are going to grow. Okay, and on a whole, entropy is always increasing. Okay, the third law is that as temperature approaches 0 Kelvin or 0 Rankine, Rankine would be the English absolute value temperature scale, entropy approaches 0. Okay, we won't deal with those very much. First law is where we're spending the most of our time for this class. This is the foundation for thermodynamics, these 4 laws of thermodynamics.